Here we have the infinite series of 5 divided by 2 to the n. So this is a geometric series with common ratio of 5 halves, which is 2.5. We know from the geometric series test that if the common ratio is greater than 1, then this series diverges. But here we want to use the integral test to show that this series diverges. And so once again, if we want to show that this series diverges using the integral test, then we need to show that the corresponding integral f of x dx diverges. And so first, let a sub n be the sequence and so the corresponding continuous function is the function 5 halves to the x. And we need to show so that this integral right here diverges. And so this integral is equal to this f of x is 5 halves, 5 divided by 2 to the x. And then using limit notation, then we can rewrite this. And then 1 to b. We have a formula for exponential function of this form. And recall that if we have the integral of a to the x dx, then this is 1 divided by ln a, where h is a constant, and then times a to the x. So in this case, the a would be the 5 halves. And so this is equal, and then the integral is going to be 1 divided by ln 5 halves, and then times 5 halves to the x. And then we need to evaluate from 1 to b. So this becomes this. So first, in the place of x, we'll put b, and then x, in the place of x, we have 1. As b approaches infinity, 5 halves to the b will approach infinity. So we have 1 divided by L ln of 5 halves times infinity, which is infinity, minus this. And this equal to infinity. And so the series, the integral right here, diverges. And therefore, by integral test, the corresponding infinite series diverges also. And as mentioned earlier, we know that this is a geometric series with common ratio of 5 halves, which is 2.5, which is greater than 1. And if we have a geometric series with common ratio greater than 1, the series diverges. But here we wanted to use the integral test to show that it diverges.